preparation for the UTME exams. Along the presentation, if you have any question, you can paste it in the comment section. It will be addressed. So, of course, before we get into the calculations and UTME style questions, we should understand the background concept behind equilibrium of forces. So it states here that it is a situation or the state of a system where all the forces this means a situation or a state of a system where all the forces acting on an object balance each other, so the object does not accelerate. So basically saying when an object or a body has attained equilibrium and either remain in its position or maintain a constant state of motion. So basically the object would be balanced. Then is the general conditions for equilibrium. General conditions for equilibrium, we can narrow it down to two major conditions. And first one is that the total force acting on an object in equilibrium is equal to 0. So basically saying if you are to sum up all the forces acting on an object in various directions, the final answer should be 0, irrespective of the type of force acting on the object. We'll see more about that as we go further down the topic. Then the second general condition is that the total turning effect, which will be discussed shortly, must be equal to 0. So the implication of it is that clockwise moment equals anti-clockwise moment. So to understand this second condition properly, what is the moment of force? So a moment of force is basically defined as the turning effect. So let's say you have this meter rule balanced on this knife edge or balanced on this pivot. You can call it a pivot or a knife edge. This means a situation or a state of a system where all the forces acting on an object balance each other, so the object does not accelerate. So basically saying when an object or a body has attained equilibrium and either remain in its position or maintain a constant state of motion. So basically the object would be balanced. Then the next thing is the general conditions for equilibrium. General conditions for equilibrium, we can narrow it down to two major conditions. The first one is that the total force acting on an object in equilibrium is equal to 0. So basically saying if you are to sum up all the forces acting on an object in various directions, the final answer should be 0, irrespective of the type of force acting on the object. We'll see more about that as we go further down the topic. Then the second general condition is that the total turning effect, which will be discussed shortly, must be equal to 0. So the implication of it is that clockwise moment equals anti-clockwise moment. So to understand this second condition properly, what is the moment of force? So a moment of force is basically defined as the turning effect. So let's say you have this meter rule balanced on this knife edge or balanced on this pivot. You can call it a pivot or a knife edge. So the moment of force is the turning effect. You should understand the background concept. Turning effect behind the equilibrium of forces. if you were to place a weight on it, it states here that the turning effect produced by a force situation about the state of a system or fixed point where all the forces, that's what the moment of force is, the turning effect produced by a force about a pivot. This means a situation, fixed point, or a state of a system generally calculated all the forces, the force acting on an object balance each other times, so the object does not accelerate distance from that point. Basically saying when an object of force is calculated, a body, the moment of force equals F times D. The unit is Newton per meter. Now, moving on from that, it is important to note that, okay, let's attempt this question, the UTME style question. So I got some questions for us to assess whether we understand each section of the topic. So this question assesses whether we understand the background of equilibrium, and it says one of the conditions necessary for an object to be in equilibrium when acted upon by a number of parallel forces is that the vector sum of the forces is, so based on the first condition, the total force acting on an object in equilibrium is equal to what? 0. So our answer is what? 0. But before we move on from this question, what's a parallel force? Parallel force speaks to the fact that you can have forces acting on an object, forces acting on an object in the same direction or in opposite direction, and the sum of all the forces at the end of the day will be equal to what? 0. Equal to what? 0. So this is what you call a parallel force. Another type of force that also helps body exhibit equilibrium would be the coplanar force. Well, we'll get to that. Okay, we'll explain parallel force. Now, let us apply the concept of moment to this question. An example, it will be our first example for moment of force. So the typical UTME/WAEC question on moment of force. So the question says a meter rule is found to balance at 50 centimeter mark. So before we dive deep, it's important to note that a uniform meter rule is taken as 100 centimeter long. A uniform meter rule is taken as 100 centimeter long. And this topic also helps us to understand that the center of gravity of a body is usually at the center of the body. The center of gravity of an object or a body is experienced at the center of the body. Now, taking that fact into consideration, if your meter rule is 100 centimeter long, then the mass of the body, which is where center of gravity of the body is also going to be located. Okay, let me take that again. The center of gravity of the body is usually found at the center of the body, and is also where the weight of the object is felt or experienced. So that's it. Center of gravity of a body is where the mass of the object or the weight of the object can be felt, and is usually at the center of the object. So the center of 100 will be what? 50. So 50 centimeter. Let's take that again. So that means from here to here, be what? 50, because 50 is the center of what? Of 100. So if nothing is added to this uniform meter rule, if nothing is added to the meter rule, then the mass of the meter rule will be felt at the 50 centimeter mark. But once they add a mass to it, this point where it is pivoted will have to change, because now the ruler is no longer weighing just 50, just its original weight. It will be weighing in addition to whatever you've added to it. So another catch about the center of gravity again is that it is felt at the center of the object. It is also where the object would balance if you can easily locate it, and that is why the pivot is at the 50 centimeter mark. So that's another extra information about the center of gravity. So let's narrow it down. Center of gravity, let's call it COG, is where the mass of the object is felt. It's also where the object can be balanced on whatever support you are trying to put it on. Okay, I think that summarizes the importance of the center of gravity, and it's usually located at the middle or the center of the object. So now, knowing all this, let us attempt this question. So a meter rule is found. A meter rule is found to balance at 50 centimeter mark when a body of mass 50 kg is suspended at the 10 centimeter mark. So let's interpret it one statement at a time. So a meter rule is found to balance at the 50 centimeter mark. Okay, I know that a meter rule is what? 100. The meter rule is 100 centimeter long. When a body of mass 50 kg is suspended at the 10 centimeter mark, so where will our 10 be? This will be our 10 centimeter. You know, it starts from 0 to what? 100. So when a mass of 50 kg is suspended at the 10 centimeter mark, so this is our 10 centimeter. So 10 centimeter. So now we have about 50 kg. So when the body of mass 50 kg is suspended at the 10 centimeter mark, the balance point is found to be 24 centimeter. So what they mean is that it was previously balanced at 50, but immediately they added the 50 kg at the 10 centimeter mark. They had to move this pivot because the ruler is now heavier than its original weight. So they had to move this pivot. The balance point is now found to be at 24. So they had to move it to 24. So we know this is 100. So they had to move it to 24. Let's get where 24 should be. So 24 should be somewhere, let's say here. Just anything to show that it is bigger than what? 10. So they had to pivot it at 24. So this is what? 24. Find the mass of the ruler. So we already know that the mass of the ruler is felt at the center. Okay, let's take it again so that it's going to be a lot clearer. Okay. Okay, we even have the diagram here. Okay. There's no need to draw it again. We have the diagram here. Well, as you can see, our analysis reflects what we also have in our diagram. Our analysis reflects what we have in our diagram. So we don't need to draw it again. So you can see the 10 centimeter mark interpreted the way I did mine also. And see where they put the 50 kg. You can see the 24 centimeter mark So I did this because I wanted you guys to see that at the beginning the pivot was at 50, but because they added the mass of 50 kilograms, they had to shift it to a new balance point, because that's what happens in real practical sessions. Your ruler is heavier than its original weight, so it won't balance again at the 50 centimeter mark it was. So they said it balanced at the 24 centimeter mark, but it doesn't change the fact that the center of the gravity of the ruler is still the same. The mass will still be experienced at the center of the ruler. So they told us to find the mass of the ruler. So in situations like this is where you now use the second condition that states that clockwise movement equals anti-clockwise movement, because immediately this mass is added here, the tendency that it can turn like this is apparent. So anti-clockwise moment equals clockwise moment. Now it is important to note that from where the mass will be to be what, 50, from 0 to where the mass will be to be 50. So the mass of the ruler will be felt at the 50 centimeter mark. So we can resolve these masses in the middle. So this place, the distance of this place, we were to look at it. Okay, let's take it out so that we can see it. So if from this place to this place is 10, and from here to here is 24, what will be this interval? Because we need it to calculate our moment about this fixed point. It will be 24 minus 10. So let's call it distance 1, let's call it L1. L1 will be 24 minus 10. So let's call this L2. L2 will be, now look at it closely, from here to here is 24, but from here to here is 50, and we need just this interval here to this place. So how do we get that? We do 50 minus 24, and that should give us 26. So our L2 is 26. So now we have what we need. By saying clockwise moment equals anti-clockwise moment, where our clockwise moment will be. So where's the clockwise moment? Let's check it together. Our clockwise moment, this is the clockwise, and this is the anti-clockwise. So clockwise will be here, this place will be M. Yeah, this place will be M, because that's where the mass of the ruler is experienced or felt. So it will be M times, what is L2? That's 26 equals 50 times, what's the distance for the second one? L1 is, okay, we didn't finish it. L1 is 14. 50 times 14. So 9 divided by 7 by 26. You should have what you are looking for. So let's do that quickly and paste what M should be in the comment section if you are following, so that let me get calculator support. Someone else can also help us do it and put the answer in the comment section. So that's 50 times 14 divided by 6. So that's 26.9. 6.9 grams. Alright, is 27. So let's check if we have 7. Okay, good. B. So our answer is B. So this is the general idea behind applying the moment of force. So let's try these steps on another question. So I'll walk you through it. I'll give you hints and let's see whether you can paste some of those answers in the comment section. So let's go to the next question. So this question is yours, and if it's a typical UTME question, you're expected to do this in no more or no less than 2 minutes. Yes, of course. So let's interpret it together. A uniform meter rule. Okay, now we know what a uniform meter rule is. A uniform meter rule. Let's interpret it together. A uniform meter rule weighing 0.5 Newton. So we knowing the weight means even though our meter rule is 100, that at the 50 centimeter mark, our meter rule weighs what? 0.5. Weighs 0.5 Newton. It will be pivoted on the knife edge at the 30 centimeter mark. So it was pivoted at the 30 centimeter mark, obviously because a mass was added to it. So that's what they are trying to tell us. Pivoted at the 30 centimeter mark. Where will the force of 2 Newton be placed from the pivot to balance the meter rule? Where will the force of 2 Newton be placed from the pivot to balance the meter rule? So, looking at the question, you already know the mass of your meter rule at the 50 centimeter mark, 0.5. So they're asking us at what distance. So you can obviously put it here. It defeats the aim of balance if you put your 2 Newton here. So logically, your 2 Newton will have to be somewhere on this side. The question is at what mark? It's obviously not going to be 30. It will be a number lesser than what? Lesser than 30. So they want to know the mark. So obviously we can get this side. That will be 50 minus what? 20. Let's call it L2. So L2 will be 50 minus 20. Not 30, sorry, 50 minus 30, that will be what? 20. So this side is 20 centimeter. But what would this side be? So if you call this side X, the remainder will be what? 30 minus X. So I believe with that we can proceed, because we'll now use our clockwise equals anti-clockwise. So we'll go 2 times 18 minus x equals 0.5 times 0.5 times 20. So opening it up to be 2 times 30, that's 60, minus 2x equals 0.5 20 what's 10. So I guess we can finish it up from here. So supposed to be your question, but I guess so. Finish it up from here. Someone should paste the answer in the comment section. So the twist there was obviously this part. Yes, this part where we deduce the x for one part. Then since we knew the entire section's length was 30, the other side will now be what, 30 minus x. Yeah, that was the twist in the question itself. So and give us the answer in the comment section what x should be. And knowing x means we also get to know the mark. So that is where the 2 Newton will be placed. So I guess we can move on to the next question, where we get the answers in the comment section. So quickly, okay, so after this session we'll get practice questions in the WhatsApp group. Let us move on to triangular forces. So the triangular forces, we are looking at forces acting on an object. Forces acting on, particularly say this is the object. Forces acting on an object and attaining what? Equilibrium. And most times they will ask you to find the tension in the support holding the object in place. This bottom is usually the weight of the object, so the weight of the object acts downward. Then majority of the time you are given angles at which the force either acts with the vertical, and sometimes they are nice enough to tell you the angles between the two forces balancing the object itself. So in situation like this, the triangular forces is applied, where you resolve the forces into triangle in a head to tail fashion. You resolve the forces into triangle in a head to tail fashion. So you go this first. Let's color them, and then you see what I'm talking about. So the head to tail fashion may not be something you get perfectly on the first try, so you try the rearrangement 2-3 more times before you get it. But this is what I mean by the head to tail fashion. So the first line will be red, pointing downward. Second one would be our T1. Okay, so this should be, sorry, this should be T2. This is T1. So second one will be the green. You want a arrow colored green pointing this way. Then the last one will be the yellow arrow pointing this way. So this is what we mean by the head to tail fashion. And then you fill up the shape. You fill up the shape with the angles that the forces make with themselves, and they also make with the words with the object. So most times you have to resolve the angles in the middle before locking it up in a triangle. So there are some questions where this method works perfectly, and there are some questions where resolving into straight up triangles like this, if you are not very careful or don't understand it very well, you may not get the right answer. So which brings us to Lami's theorem. Lami's theorem works irrespective of question. So far it's a question that involves three forces acting on an object to maintain it at equilibrium. Lami's theorem works perfectly. Emphasis on three forces interacting with an object to keep it at equilibrium. So how does the Lami's theorem work? So let's look at it closely. So looking at, okay, we understand all this now. So as I said, this place is T1. Let's call this place T2. So let's say okay, let's call this alpha. Let's call this, let me change the position a bit. Not that it matters really, but let's call this alpha. The angle on this side alpha. Call this beta, and then the angle here be gamma. All Lami is saying is that irrespective of, as long as there's a three forces acting on a system acting on the body to maintain it at equilibrium, this expression works fine. The angle facing the side, the angle face opposite the side, and the angle opposite the side can be expressed like this. So the first one will be T1 sine alpha. Second one will be T2. So the beta is facing cos T2. That will be sine beta. Then the last one, the weight, the gamma is facing it. So you can call it weight divided by gamma. So this right here is the Lami's theorem. So this prevents you from having to be looking for head to tail fashion, you know, that some of you get wrong, and even waste time unnecessarily. At a glance, in the space of 2 minutes, before you resolve the angles properly, this Lami's expression solves the question, and we're about to see it in full effect. We're about to see it in full effect shortly. So let's look for questions. I think I have one stored. Okay, perfect. So looking at this question, the first thing expected of us is to resolve the angles. So if this side is 60, then obviously alternate angles are equal. This side will also be what? 60. If this side is 45, alternate angle, this side also going to be, let me change the thickness. This side will also be what? 45. So now taking this, you know, imaginary line to complete a straight line with this, we can find our, you know, we call this side the alpha, or in this case, because it is the T2 is the side facing this angle, we can call it beta. The side facing T1 alpha. Our gamma is already here as 60 plus 45, that's 105 degree as gamma. So this is the hint. Taking this imaginary line that we've been using to resolve the angle as a straight line to this weight, we can find this remaining one as angle on a straight line. So beta will be 180 minus 45, while alpha will be 180 minus 60. So if you have any question at this point, you can paste it in the comment section to be explained again. So just for the sake of clarity, let's look at it. The first force acting this way, the second force acting this way, the third force acting this way. Then because they only showed us the angle that the force, the angle at which is acts to the horizontal, to the vertical, sorry, to the vertical. But what we need is angle to one another, even angle to the what, to the weight acting downward. So we used alternate, that if this place is 60, to the imaginary line, this place is 60, this place, sorry, in this place is 45. Okay, taking this question again, we know now that completing an imaginary line here, this place is 60, this place is 45, so the total angle, which is our gamma, is 60 plus 45 is 105 degree. Then we can get this place, okay, because this was the T1 and this is the T2. We can get this T1, our alpha, as 108, 180, sorry, 180 minus 45. 180 minus 45, that should be 135. And our beta, so looking at it as a straight line again, our beta will also be 180 degree minus 60, that's 120. So having these three angles, 1, 2, this is 135. And this side is 120. So having these three angles, we can now use the Lami's theorem. Use the Lami's theorem. Lami's theorem again, for some of us that haven't gotten it yet. It saves time for questions like this. T1 sine alpha, T2 sine beta, weight over sine gamma. So substituting, we know this. So usually you use the known because you know the weight, you know the gamma. You use it to calculate against the unknowns. So you pick one of these and compare it to this one after the other. So So let's continue. with the substitution. So we do W weight over sine gamma equals, let's say we're looking for T1 first, sine alpha. Substituting directly, our weight, I think in the question, our weight was 100 Newton, good. So 100 divided by sine gamma is 105 equals, what we are looking for, one of them, because it will also find, question says we should find both T1 and T2 and the alpha. I think let me look at the question again. Alpha should be 135. Alpha should be 135, so sine 135 degree. Okay, someone can complete it for us so that we can get a move on. So sine 135 degree. So we cross multiply, T1 will be 100. So 135 degree divided by sine 5 degree. So that's our T1. You can see this is something that will take you less than, let's say, 1 minute 30 seconds, less than 2 minutes. We see questions like this. And the good part of UTME physics is that not all questions are calculative. They ask normal concept-based questions, and then at least 40% of the questions is calculation. The rest is usually concept-based. So things like this shouldn't take more than 2 minutes of your time, and your calculator can do rest from here. Some of you will be wondering, but there's no sign on the calculator. How do we do 135? So obviously we did 180 minus the sine 180 minus 35, which is 45. So this place, you know that challenge that of not having sign on your UTME calculator, you will do 100 times 2 sine 180 minus 135. I know that sine is positive in the second quadrant, so all over this one too will be sine 180. Okay, the only one there I would give ish is this 105, but let's just solve it normally. Let's solve it normally. So this one is going to be 75. We subtract it from 180. Yeah. So one can do this for us in the comment section and give us the answer. So that will be 135 divided by sine 105. So the answer you get will be your T1, and then you just repeat the process again for T2. So for T2 also, it will be T2 divided by sine beta equals W over sine gamma. So basically using the known, calculate the unknown. So someone can try T2 and show us in the comment section what T2 should be and what T1 should be. So in decimals, can give us in decimals. So we just want to understand how to use the Lami's theorem at this point. So let's look for your assessment. So this is where the class ends with this question. You can attempt this. We're just analyzing it. What you've been doing is what you do. Okay, let's take it over to that page 60, 150, 100. So what we have is let's draw it. We have something like this. So you said say 60, F1 force 1, F2 force 2, obviously acting opposite direction, and then mass or the weight 100 acting at 105. So it's the same thing. Your Lami's theorem would work perfectly here also. So this is what I was talking about, that Lami's theorem works as long as you're dealing with three forces acting in different directions to stabilize a particular object or to maintain an object at equilibrium. So all you have to do, this is obviously going to be your gamma, because it's the one nearly opposite to the weight of the object acting downward. So 60, 60. Then this will be your, this is F2, whatever you get here. So how do we get the angle on this side? We can put what the angle on, or what beta should be. So obviously this is the alpha. Alpha is 105. So what should beta be? You can tell us how to get beta, or someone should put in the comment section what beta is. So beta would be, okay, let me give you like a minute or two to figure out what beta is. Okay, because of time, I think we need to round up. So our beta would be obviously 360 minus 105 plus 60. Yes, whatever you get here will be your beta. Then you can apply Lami's theorem to your beta. Okay, let's do it together. So it'll be 360 minus 105. So your beta would be 255. So the idea behind finding the beta like this is that angle at the point is what? 360. Angle at the point is 360. So you know this part, but you don't know. So you know this part, but you don't know the third part, and it's at a point. So this is the end. From there go T1 over sine alpha equals T2 over sine beta equals obviously your weight, okay, your weight over sine gamma. So use the known to find the unknown. That way, speed things up. Triangle over forces. So Lami's theorem is the secret to those type of questions. If you have any question at this point, you can drop it in the comment section. We'll address it and then we'll discuss further in the WhatsApp group. If you still have other areas you don't understand. Thank you very much for staying through to the end.